A very good morning. Am I audible?
Yes, sir.
Okay, let me share the screen. Yeah. So you are able to see the screen?
Yes, sir.
Yeah. So today we are going to start with a new topic, but it's not entirely new. You are well known about this. What is the meaning of partial derivatives? Okay. And we have also studied ordinary differential equations in the function of single variable case. Okay, the last semester. Now, we are going to look at the theory for partial differential equations, and we will now also try to see what kind of real life applications for this partial differential equation in exist in physics and the engineering fields. Okay, uh, that we will try to address whenever the time will allow. Okay, right. And of course, uh, we are going to again recall those concepts like order, degree, and all of the differential equations. But you have learned in that uh, order differential equation. The similar concepts are going to be applied here for analyzing or for classifying the order and degree of a given partial differential equation. Okay. Now, the very first thing is we are now no more in single variable case. So means we are going to have at least two independent variables. Okay, in the means okay in the equation. Okay, so if you have more than two or more independent variables, so if you differentiate, you will definitely uh, go through with the partial derivatives and that will means if you differentiate a family of surfaces, for example, you have a like a spherical surface, okay, like you have this is x square plus let's say y square plus some z minus c whole square equals to a square. I've taken this particular example because it's going to be occur in this little moment again. Okay? And you have a so this will denote the family of spheres. So as c varies, so a is you can say fixed or c is also fixed. Whenever a and c will vary, you will have a family of spheres. Okay, and to know that is going to be the solution of what type of partial differential equation, how to proceed. Okay, and the questions like whether the corresponding differential equation which you are going to derive from this equation, suppose you have started with the family thus and you derive the partial differential equation associated with this problem. So the question certainly will be there that whether this family is only correspond to that partial differential equation, or there are other families also which may be the which will also be the solution for that partial differential equation. And in what case the differential equation has unique solution, okay, means there is no other solution except one. Okay, so those questions we will try to answer. Okay? Right. So let's go through with the some theory. So it's as mentioned, so a PD. So PD in short form will name that partial differential equation as PD is an equation that contains one or more partial derivatives of an unknown function z that depends on at least two variables c and x and y. So means I generally means like you have seen in the vector calculus we most of the work with the surfaces z equals to f of x comma y. Okay. So so most of the time we will take this z as a dependent variable and x and y are independent variables. So you have two independent variables. You can extend as many as you want. Okay. So z is depends on, you can say x comma y comma some let's take instead of x comma y you can also take x1 x2 x3 and so on xn. Now so so we are talking about a partial differential equation. This is a equation of surface, not a partial differential equations like we have this family of spheres. It's not a partial differential equation because there are you are not able to see any partial derivatives here. Okay? So definitely partial differential equation is an equation where the partial derivatives will occur. Okay? So so you have in the general form, if I want to write it as this is a function of, it's going to be right hand side, you put equals to 0. Everything you put on the left hand side and right hand side is 0. Okay, so where the left hand side will be possibly the function of let's say 2x comma y. Okay, another means like you have this is p, okay, u and so on. Okay, so means like I'm just giving you one example, x comma y comma t, and you have or instead of the, let's take with two variables x comma y comma z, zx, zy, zxy, okay, and so on. So here this bracket will not end. Okay, I'm not ending with this bracket. I'm just putting the dot dot dot. Okay, zxy, zxx, zy, zyy, dot 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 equals to 0. So these dots means is this there may be these are second order partial derivatives. Okay, so there may be also available the third order partial derivatives also may occur in the equation and so on, and any higher order derivatives. Okay, now depends, now we will see the classification of these, means we will restrict with us up to second order, okay, partial differential equations. Okay, we will restrict ourselves till second order partial differential equations. So I will write mostly now I will write what here is, I may now close bracket because we are going to more focused on this. Okay, now this is we will denote the further notation also I wish to mention here. Zx is dou z by dou x. You see, I hope these all notations are very much clear. The second thing is, which you may also again ask, that what is zxy and what is zyx. Okay, since in the partial differential equations case we are keeping in that mind that mixed derivative theorem should be applicable. Okay, means the first order and second order partial derivatives are continuous. So zxy or zyx both will be the same value. Okay, so we are having that additional assumption here. So I hope now there should not be any doubt about it. Now what is zxy or zyx? Because both way, if you do first x then y or first y with then x, okay, choice is yours. Now the notations, further notations, zx, the first partial derivatives p, we denote it by zy, we will denote it by q. Okay, and this zxx we will denote it by r. This zxy will denote it by s, and zyy we will denote it by p, pqrst. Okay, so these are the standard notation in the textbooks, okay, which you may follow. So this maybe you have seen in the when we discussed the maxima minima, okay, for a function of two variables as well. Okay, now the next thing is like means it's a if the second order derivatives are involved, okay, that's just means involved, not doesn't mean involved, means the highest order derivative is of second order. Okay, so it's going to be possibly the second order partial differential equation. If the highest order derivative occur is first order, it's going to be possibly the first order partial differential equation. Why I'm making here the specific thing is possibly, okay, because you have to take care about the radical terms which we have discussed in detail in the ordinary differential equations. So I'm not going to discuss them again here. Again, the degree of the partial differential equation also depends on the index of the highest order derivative, the index of the highest order derivative present in the differential equation. Okay, so a similar study will be applicable here. Okay, so there is no need of discussion about it. Okay, of course we will see that when it is linear, non-linear, so there is another additional name is quasi-linear, almost linear. So we will try to classify the first order partial differential equation or second order partial differential equation accordingly. Okay, right. So we are not more focused on this is second order or third order. We will try this here. We are not trying to address, but whenever we are talking about the specific problems, okay, then we will try to address that is second order, non-linear or linear or what type of things. Okay, right. Now let's proceed further. So this is what we have just now spoken. So I may list out all the examples, okay, which you may have also seen during your tutorials, okay, that means which are some models like wave equation, means you have seen the solution of the wave equations, okay, some type of solutions, okay, f of x plus cta plus f, okay. So similar heat equation and Laplace equation, Poisson equations, these are very famous partial differential equations, okay, and you will see the most of the second order differential equation when we will talk about in terms of canonical forms, okay, that I'm using here word that canonical form here, but it may come later, but the second order differential equation will always be, you will always be able to reduce them in one of them, okay, one of this specific type of this, okay. So a canonical form will give you a transformation. What does it mean is it will give you a transformation which will transform the original second order PD into some specific form. It may either give you the wave equation, or it may either give you the heat equation or Laplace equation, for which you very well know that how to solve such type of problems. So that we are also going to see in detail. Also, we will try to address some of the realistic phenomena which will reduce to the wave equation, whose corresponding governing equations are going to be wave equation, similar for heat equation. We will try to address them also. Okay, that will be little later when we will talk about the second order partial differential equations. Okay, that will be in detail later. and we will also discuss the solution part of it, means how to solve these type of problems. Right. Now, so first we will start with the first order partial differential equation. So first order partial differential is automatically should be in your mind that in the given differential equation, the highest order partial derivatives is at most one, not at most, it's exactly one. Okay, the order. Okay, so means the equation is a first means it's a very now simple statement. Now if first order PD in two independent variables and one dependent variable z is an equation of the following form. Okay, so these functions x, y are independent, z is depending on x and y, and here is the first order partial derivative. This is first order PD. Okay, it's a linear, non-linear, that we will discuss. Okay, right. Now, as I mentioned already, so zx we denote it by p, and zy I will denote it by q. Okay, so these are the standard notations. I'm just trying to mention here again and again. Okay, so that in later stage you will be comfortable with respect to studying any textbook. Okay, now the next question is what means this, how the solution will be. Okay, what will be the possible solution? Okay, or see, by looking at this equation, what you can think is the solution will be in some region. Okay, some region R. Okay, solution will be there in some region R. Solution, what type of, either solution is z equals to f of x comma y. Okay, or means it may be, it may not be this. Okay, what it may be is possibly some f of x comma y comma z comma a comma b, that you will see later on. It's going to be a, so means it's going to be a general solution. Okay, and you may also see that like in the ordinary differential equation case, if you talk about the general solution of ordinary differential equation of first order. Okay, so general solution will have one arbitrary constant. Okay, but when in case of first order PD, okay, so that if you talk about first order PD with respect to two independent variables, that its general solution will have two arbitrary constants. There is one independent variable, here is two independent variables. Okay, so means you will see later that the solution will have two parameters. Okay, or you have two arbitrary constants, that we will see. Now what you need to essentially put the condition is, means it has all the first order partial derivatives and it should satisfy the equation in that region R. Okay, so this function should be nice, means in terms of that it has first order partial derivatives and it should satisfy the equation. Okay, so that's a rough definition, you can say, roughly we can speak that. Okay, so this is what here I have written. That's the solution of a PD in some region R of the space of the independent variable is a function that has all the partial derivatives appearing in the PD in some domain D containing R and satisfies the PD everywhere in R. So I hope this is a general statement, not for the only first order PD. This is the statement for any order, with any higher order PD as well. Okay, so it says that of the space of the independent variables, means that there may be two independent variables, there may be three independent variables, and so on. Okay, and it will be a function that has all the partial derivatives. So here first order partial derivatives occurs, it has a first order partial derivative and satisfies the PD everywhere. So it should satisfy the PD everywhere. This is a very rough statement, you can say. Now, what type of conditions required, that we will see later. Okay, as we have seen in the ordinary differential equation case, okay, single variable case, there was a very famous result, okay, which gives you the existence uniqueness, was Picard's theorem, if you recall. And you have seen that how it was, it means Picard's theorem on a rectangular region again. Okay, so how it was difficult to construct the solution there. Okay? So we have seen that, okay, that in detail there. So so these things will be more complicated when you are talking about the partial derivatives, okay, partial differential equations. So we'll see how much theory we can address here, okay, right. Okay, so here is the means the family of a sphere centered at 0, 0 C with radius a. Okay, so where a and c are arbitrary constants. So if I wish to obtain the associated partial differential equation with this family, okay, so of course we have to differentiate partially, okay, and we are assuming here, so in general we will assume z as a function of xy. So z is dependent and x and y are independent. So that is the assumption, okay. So that's the assumption. Instead of that, you can also work with x as dependent and y and z are independent. That also you can work. So but here after we will assume that z is dependent and x and y are independent. So when you differentiate partially with respect to x, so what is other objective is, the first objective is to get associated partial differential equation, okay, and second objective is to have you have to get rid of this arbitrary constant in the final equation, okay, those should not present. Now differentiating partially with respect to x, what it will lead to if we apply the chain rule and everything. So 2x plus, if we differentiate partially with respect to x, so this is plus 0 plus 2 times z minus c times zx is equals to 0. So this implies you have this implies z minus c is equals to minus x by 2. Okay, so when you differentiate partially with respect to x, you have got this. Now when you differentiate partially with respect to y, what you will get is, in this is symmetric, okay, or you have this is 0 plus 2y plus 2 times z minus c times zy equals to 0, and that will lead to z minus c is equals to minus y by q. Now as I mentioned, that we have to get rid of this arbitrary constant c as well. How would you do? So from these two equations, z minus c equals to this, z minus c equals to this. So this both should equal. Okay. So this implies minus x by p is equals to minus y by q. And you may write now minus x by p equals to minus y by q. Now this implies you have py minus qx equals to 0. So this will be the associated partial differential equation. So when you have two parameters, note that you are going with first order partial differential equation. Okay. When you have more than two, you will go with the second order. Means like more than two means up to 4. Okay. Right. Now this is an idea here. Okay. Now, so as I mentioned, so this is the associated partial differential equation. Now we will try to answer whether this is the only family which is the solution of this partial differential equation. Okay, so the answer is no. Okay, so that so for that you consider this following this right circular cone. Okay, the family, the set of all right circular cones. Okay, so this will decide, this will give you the right circular cone. So you have some alpha angle. Okay, alpha is, so you have z as 0, 0 c, you have, okay, so you have something like this right circular cone. Okay, now this is So now your job is to now verify whether this is going to be the again equation. Okay. So for that, what you can do again you will proceed in the similar manner. Okay, so if you differentiate partially with respect to x, what you will get is 2x equals to 2 times z minus c 10 square alpha time zx, so that zx is p, so 2 will get cancelled. So what you will get is this will implies x by p is equals to z minus c times 10 square alpha. Similarly, you can differentiate partially with respect to y. So 2y is equals to and so on. So what it will give you is this is equals to y by q. Okay. So that you can find out. So that now x by p equals to y by q will lead to this equation. Now, so what was the previous family? Was the sphere. Okay. With the sphere centered at 0, 0, C. So what is the common thing behind between them is nothing but the it's a type of revolution about the z-axis. So z-axis is the axis of revolution. Okay, this is a common thing. Okay, so this is why this happened. Now, if you want to give a general form of this, so you can certainly have the family is like z equals to, so it is this all such type of families fall into this square root of x square plus y square function of this arbitrary function of this. So this family will give you again the corresponding PD that also you can verify. Okay, so that we can also again we can also verify that. So associated partial differential equation to this family z equals to f of square root of x square plus y square. So f is an arbitrary function. Okay, now this is going to be now differentiate partially with respect to x and with respect to y. So zx equals to, you have f dash of square root of x square plus y square time. So it differentiate of this 1 by 2 root of this and the x, and so this is x divided by square root of x square plus y square. Similarly, zy is equals to y time f dash of square root of x square plus y square divided by square root of x square plus y square. So from here and here, what you can observe, so this is a p by x equals to q by y. So these together equation, this implies p by x is equals to q by y. And so this will implies py minus qx equals to q. Now earlier families were having two arbitrary constants and here is one arbitrary constant. So that will also give an idea that if you are going to work out with a family which involved one arbitrary function, okay, that only, okay, which involves one arbitrary function, that will lead to the first order partial differential equation. Similarly, if you have two arbitrary functions involved, suppose f of x plus g of, or means like okay, two arbitrary functions. So for example, let me give you one example here. Okay, you may work out with this. Z equals to, let's take f of x plus ct and plus g of x minus ct. Okay, so it's involved are two arbitrary functions f and g. Okay, so you have to certainly find out the second order PD. So you can we will okay, so you can differentiate 2 times with respect to x, 2 times with respect to y, and we will be able to get it. Okay, so what it will this is going to be, I hope this is going to be dou square z by dou x square is equals to c square times dou square z by dou t square. Okay, so wave equation, this is solution of the wave. So one arbitrary function correspond to one order. Two arbitrary constant correspond to first order partial differential equation, and so on. Okay, right. Okay, so whatever we have discussed, so this is what is written here. So the common thing between the spheres and the cone is that they are surfaces of revolution with the z-axis as the axis of symmetry. That's fine. Okay. So all such surfaces of revolution can be characterized by the following equation. That you can do that. Okay, and show that the corresponding PD is this. So that we have okay, that we have right. So okay. Now, note that the considered families are of the following type of function equations. So you have two parameters where A and B are arbitrary common. Okay. So what is the procedure here now? Again, so Z is dependent and X and Y are independent variables. Okay. So what you do is, what you have done is, first you have to differentiate partially with respect to X and Y. Okay, so what it will give you by the, you can, if, that chain rule, f with respect to x plus p time fz equals to, so right, you differentiate partially with respect to x. What would happen? So you have to differentiate f with respect to x, and x with respect to x derivative is 1 plus fy, y derivative with respect to x, plus f z, z derivative with respect to x equals to 0. Now, since y is an independent variable, so y derivative with respect to x is 0, so this term will not be there. X with respect to x derivative is 1. Okay, this is 1. So fx plus p time fz equals to 0. Similarly, fy plus q time fz equals to 0. Okay, now what you do, what is the next step is, you have to eliminate arbitrary constant from above three equations. You have three equations. You have to eliminate now arbitrary constants A and B, and you have to find the associated first order PD in the following form. So where these arbitrary constants will not occur again. Okay. So that is how to remove that. Okay, how to eliminate this arbitrary constant, that only will come through the practice. Okay, right. So now let's classify the first order PDs now. Okay, so if you have any question, you can ask. If you have any question, you can ask. Okay. Okay, so let's proceed now. Now, see, you have the original equation, partial differential equation is of the form x comma y comma z comma p comma q equals to 0. Okay. Now, so there are various possibilities to write this type of equation. So one of them possibility is, you have, this is p, okay. Dou z by dou x is a small p. Dou z by dou y is small p. Okay. So there are various possibilities. This is first order differential equation. Okay. The very first thing is p to the power 1 and q to the power 1. Hence you have the index of the highest order derivative is 1. Okay. So these are all are possibilities, okay, not necessary. Okay, so you have this is means if you are able to write this equation in the following form, means you have some p, means the first order partial derivative with respect to x plus coefficient of q is equals to the right hand side. So these coefficients involve only x, y, and z. Okay, all these brackets are the only possible functions of x, y, and z. Then this such type of partial differential equation, first order partial differential equation, is known as quasi-linear. Okay, now means, see, if you try to relate with the ordinary differential equation case, okay, why you are not talking about say linear one, I may answer here that because it may also involve the product of z and its derivative. So if you recall, in the ordinary differential equation case, when you will say the linear and non-linear differential equation, so it means you are for the linear case you are not allowing the product of y and its any of its derivatives. Okay, so this is why here it is not written as non-linear, but it's type of quasi-linear, because these are special type of equation which can be solved by some method which we will try to address them. Okay, so here in the quasi-linear, it is you are allowed to have the product of z and any of its derivative. Not only z, any power of z or any function of z, e to the power z also fine, or cos z is also fine. Okay, and so on. Okay, so here if this is allowing, but its definition is not a linear, it's a quasi-linear. Now, if you drop this, means what you drop is you remove this z here, means the p and q coefficients are only function of x and y. Right hand side you don't care, they may also a function of x, y, and z at the most. Okay, the left hand side p and q coefficients are functions of x and y only, z is not involved. Then we will say it's a almost linear PD, not linear again. Okay, so you will see it is a almost linear when you have p and q coefficients are function of x and y only. Right hand side could be function of x, y, and z. Okay, now so that is a definition of almost linear PD. Now to make it fully linear, what is required now? You have to focus on the right hand side. Okay, so if the right hand side is linear in z, means if the right hand side is of the form of something like some c of x comma y is a function of x and y plus d of x comma. Okay, like of is a z to the power 1 at the most, and its coefficient is function of x. And there may be additional t of function of x comma y or a constant. So if the right hand side also is of this type, this is a linear in z, okay, then in addition to the almost linear case, means p and q coefficients are x and function of x and y only, and the right hand side is linear in z, then you will say is a linear PD of first order. Okay, right. So what is the, so equation of the following form is said to be an almost linear PD of first order. Means you can see the right hand side is allowed to be a non-linear in z. Okay, this is why it is said. Okay, now if you don't allow that, means the right hand side is a linear in z, then you'll say this is called linear PD of first order. Okay, so linear in z, so cxyz, so you can push that on this right hand side as well. So you have this is minus c of x comma yz plus d of x. Okay? So either way, or you can put this on the left side. Okay, so linear in z, P and Q. Okay. If it is linear only in P and Q, it's a almost linear. Okay, right. Now, if you are if any one of them is not happening, means all of them are not happening, means we will say it's a non-linear. First order PD is non-linear. Given PD is non-linear. Okay, if does not fall in above category. Okay, right. Now let's look at the problems now. See, problems means we'll try to address the classification of first order PDs by looking at some example. Okay. Now, if you look at this problem, so answer is also given, okay, in front of that. But why it is so? Let us see the P coefficient Q. So first you have to focus on the left side. Okay. Or you can also focus on the right side, but first you focus on left side. Now P coefficient is function of X only, and Q coefficient is a function of X Y only. Means they are not involving Z. That's why you have to see. Okay. Now means they are not involving Z. So they are at most a function of X, Y. Now the right hand side. Right hand side is linear in Z. It's look right, because Z to the power 1 and Z coefficient is function of X and Y. So it's a linear PD of first order. Now let's look at this equation. So again, the right hand side, left hand side, P and Q coefficients are function of X and Y only. And right hand side is not linear in Z. So in other words, we can say it's a left hand side is a linear in P and Q. Okay. What do you mean by linear in P and Q? Means P and Q coefficients are functions of X and Y only. Okay. Right hand side is not linear in Z. So it's a almost linear PD of first order. Right. Now, third equation, if you look at here. So the right hand side or left hand side, P coefficient is involving X, Y, and Z. So first term itself, P coefficient is function of X, Y, and Z. Means it's neither almost linear nor linear. Not a linear case. So it may possibly be a quasi-linear. So now for that you need to see the second term. Second term coefficient is involving X, Y, and Z. That's fine. And the right hand side is now function of X, Y, and Z. So it's a quasi-linear PD of first order. Right. And this is an example of a non-linear PD because it's not linear in P itself, because P square is there. Okay, so P square is there, or Q square is there, or P into Q is there. So it's a non-linear PD of first order. Okay. Right. Okay. Okay. So it's like now how to get the PD for the associated problem. Okay, this is another way. Okay, which may relate further a very standard equation known as Lagrange equation. Okay, so this is why we are having this derivation here. Okay, so consider the following relation, and you want to find the associated partial differential equation. Okay, so where u is a function of x, y, z, v is also as a function of x, y, z. Okay, now as mentioned, we are assuming that z is dependent and x and y are independent variables. Okay, so that is a very clear. So it's a further generalization of this geometric entity, so that's okay. So this is a very general one. Not only this, it's a general for many problems. Right. So now, how to proceed? So you have to differentiate partially with respect to x. So if you differentiate partially with respect to x, treating u and v as a function of x, y, and z, what you will do is you differentiate partially with respect to x. What it will give you? Fu. First, you differentiate partially with respect to u, then u with respect to x. So you have, this is u u with respect to x. So you have ux right. So this is so this is ux fu ux. Okay, so we have to differentiate first the partially with respect p with respect to, right. Okay. So fu ux plus fv dx equals to 0. Now what is this is, now this is fu ux is what is ux is this is p partial derivative, because it's a function of x, y, and z. Okay, px plus and py with respect to y with respect to x, pz z with respect to x. So that's going to be zx is we have denoted by p plus fv time psi x plus psi z q. Not q is going to be p, right? Equals to 0. Now instead of this p, you can also use u. Okay, it's not a, if u is a function of x, y, z, so it's I will use this notation as, okay, so that okay, this is instead of this I have, this is ux uz, this is vx vz. That's also fine. Okay, rather going with another notations, let's go with this. Okay, so just u is equals to u of x, y, z, v equals to v of x, y, z. That's denoted by this. Now similarly, if you differentiate partially with respect to y, what you will get is the following. This is symmetry now. Uy plus uz q plus fv vy plus vzq is equals to 0. Now these two equations. So if you write in the corresponding matrix form, what it will be is ux plus uzp, vx plus vzp. It's a first row. Second row is uy plus uzq, and you have, this is vy plus vzq time fu fv equals to 0. Now what we are interested in, we are interested in a non-trivial solution. Okay, we are interested in a non-trivial solution of this problem. Okay, now if the determinant of 0 means it is non-singular matrix, the left hand side coefficient matrix is non-singular, then you have only trivial solution, only 0 solution possible, right? I hope that is you are aware about it. Okay, so for non-trivial solution, what you require is this determinant should be 0. Okay, so for non-trivial solution, what we must have is this determinant of ux plus uzp, vx plus vzp, uy plus uzq, vy plus vzq is determinant equals to 0. Now you know how to solve this determinant is, now you can right, you can go get it. So let me on the next page. So the determinant is ux plus uzp time vy plus vzq minus vx plus vzp ux plus uy plus uzq equals to 0. Now you arrange the coefficients of P and Q. So let's work out. So you have uz, vz, pq with minus uz minus vz pq will get cancelled. Okay, so what you will have is ux vy plus ux vzq, right? First is this, so plus uz vy p plus uz vz p into q. What about the second term? Minus vx uy minus uy vz right, p minus vx uzq minus uz vz p into q equals to 0. So this term will get cancelled. Now, what is the p coefficient? So p coefficient is you have uz vy minus uy vz, okay, plus q coefficient is ux vz minus vx uz, okay. So this is a p coefficient, this is a q coefficient, equals to, I'm sending all the things on the right now. So on the right now, this will work on the right. So vx uy minus vx uy minus ux vy. Now further, if you look at this carefully, this is nothing but Jacobian of uv with respect to zy. I'm just writing here Jacobian of uv with respect to z comma y, p plus q coefficient Jacobian of uv with respect to x and z. If you recall all these things, okay, we have already done this thing. Okay, plus Jacobian of uv with respect to x and z. Q is equals to Jacobian of uv with respect to x and y. Okay, so we have to be careful about it. I think yeah, there is some so what is Jacobian of uv with respect to zy is uz uy vz vy. So vz uz vy minus uy vz. So that's fine. And this is ux. This is a okay. This coefficient is determinant of ux, uz, vx, vz. So ux, vz minus vx, uz. That's fine. And the right hand side is you have ux, uy, vx, vy. So you have this ux, vy minus uy, vx. So you have here y comma x. Okay, so these are this will be the associated partial differential equation corresponding to that general. Okay, so you can I can also verify with respect to now any problem. Okay, right. So we have all these things we have done. That's fine. Now this equation is called Lagrange's PDE of first order. Okay? So this equation is known as Lagrange's PDE of first order. Okay, so we have obtained, I think, yz and this is zx. Okay, so so here you can see this is these are here y comma z, we have obtained z comma y. This is z comma x, we have obtained x comma z, and this is y comma x. We have obtained so we have this x comma y, we have obtained y comma x. So if you multiply that above by minus sign on the both side, you will get this. Okay, so that's not a problem. Okay, so this type of equation is known as the Lagrange's PDE of first order. Right. Let's do this example. This is instead of I, because we have not done the complex variable. So you just take I is a constant. Okay, I is equals to some C. Okay, so we have these arbitrary functions, two arbitrary functions. So it will go to the, it will correspond to the second order partial differential equation. Okay, so for doing so, you have to differentiate now partially with respect to x and partially with respect to t. Okay, so immediately after looking at the problem, you have to get in your get that intuition that since this is involving two arbitrary functions, you have to go for at least second order derivatives to eliminate them. Okay, now differentiating partially with respect to x, what it will give you. So zx equals to f dash x plus it plus z dash x plus it. Okay, in fact, if you go with the zx x, you have second derivative x plus it plus z double dash x minus I, right? Now you can also find zxt. Okay, these functions you have to assume that f and g are continuous functions. Okay, all partial derivative, all second order partial derivatives are continuous. Mixed derivative theorem applicable. So you can also find out zxt. Means you differentiate, you have already have first order partial derivative with respect to x, you differentiate with respect to t now. So what you will get is I time f second derivative x plus it minus I time z double dash x minus I. Now differentiating partially with respect to t, what it will give you, zt is equals to I time f dash x plus it minus I time g dash x minus it. Now again, if you differentiate ztt is equals to I square f double dash x plus it, okay, minus I square g double dash x minus it. Right? Minus minus here plus. Right? So this is going to be now, if you recall, this is going to be I square time f double dash x plus it plus g double dash of x minus it. And that, you know, if you are look at above, that's going to be zxx. And this is c square zxx. Now, note that this is c constant is fixed, not arbitrary. Okay, we have assumed that c is a constant is fixed, not an arbitrary constant. Okay, and this will correspond to, you know, wave equation. Okay, so you have the one solution for the wave equation. Now let's this is already done, so right. Now let us consider another example. So ax square plus by square plus z square equals to 1 is kind of, you know, right? You have, this is a kind of ellipsoid, right? Now, find its PD. So you have two arbitrary constants. Okay, so you will go for the first order PD. Okay, now differentiate partially with respect to x. What you will get is 2ax plus 2 plus 0, second term derivative with respect to x, 0, 2z, zx, dou z by dou x. That's going to be part p is equals to 0. We'll get rid of this. From here, what you will get is z by a is equals to minus x by p. Right? Now similarly, if you differentiate partially with respect to y, what you will obtain? Partially with respect to y, if you go with this, you will have 2by plus 2z cube is equals to 0. So this will give you, so this will imply z by b is equals to minus y by q, right? Yes. Now you have so you have equations now. So what are equations now? Z by a is equals to minus x by p, and z by b equals to minus y by q. So b. and you have ax square plus by square plus z square equals to 1. Now you have to eliminate these two arbitrary constants from here. Yes, how to eliminate them? There are three equations. You have to eliminate A and B. Yes? It's very simple.
We can take A's value from the first, B's value from the second, and put it in the third.
Yes, exactly. Yes. So it's a very simple process here. So from here, it's the first equation. You can have A is equals to, you can take A this side and you have a minus PZ by X, and I think B is equals to minus QZ by Y. Now you substitute these two in this equation. You have eliminated. Right? So I use a substitute here. Now what you will, the corresponding now is you have minus pz by x times x square minus qz by y square plus z square equals to 1. This one x will get cancelled, one y will get cancelled, and now finally you have z square minus z time px plus qy is equals to 1. Yes, this is it final. So this is what we have obtained, right? Z time px plus qy is equals to z square minus. So this is the final. Okay. Now, fine. So let me give you another example. Okay. So just now we have solved. Okay. This is u. This is v. Okay. You try to identify now for this finite BD. So you can take it as an exercise. Okay. So I will float these 3 to 3, 4. Okay. I will give you the solution as well. Not a problem. This is the final answer. And okay. So for this, yes. So I will plot these 3 problems. Okay. On the Google Classroom. Okay. You try to find out the final answers or match with the final solution. Okay. Okay. If you have any question, you can ask. We can stop here. Okay. No questions. Thank you.
Thank you, sir.
Thank you, sir.